Check it out now, y'all.
NanoHub U, online instruction.
We're finally in a position where we can discuss quantum statistics, and we can finally describe the difference in probabilities that govern the occupation of quantum particles compared to the probabilities that govern classical particles that are distinguishable one from another. In this lecture, we're going to backtrack a little bit. It turns out there's a very simple way to make you understand or appreciate the difference between classical statistics and quantum statistics. And the way to improve your appreciation of the difference is to return back to our problem where we had 6 particles, and we distributed those 6 particles in these 10 energy levels, and the energy levels were each separated one from another by this quantity epsilon. And we treated that case about 2-3 lectures back. If you recall, we generated a table that lists all the possible states of these distinguishable particles, and it also listed the number of microstates, or the multiplicity of each state that was possible. So in this lecture, it's I think it would be very helpful if you printed out this slide. It's this table. It's actually given to you in the on the website, right? Because we're going to refer back to it, and we're going to try to understand how this table is modified when we make the particles indistinguishable. So what we're going to do now is we're going to remove the color from the particles. Before, each particle was colored a different way so we could distinguish them. Now we're going to make all the particles the same color, right? And we're going to say we take these 6 particles, we put them in this system. We're going to constrain the total energy to be equal to 9 epsilon. That's the same constraint that we used when we considered this, when we generated this table. So we're trying to compare and contrast the indistinguishable case with the classical distinguishable case that we generated when we first wrote down this table. So that's the plan, and then when we're finished with the Bose particles, so these particles have 0 spin or integer spin. When we're finished with them, we'll also consider particles that are indistinguishable but have spin 1/2, and we'll talk about the difference in the way the particles can occupy these states that's related to the quantum nature of the particles. So what we have to do is we basically have to go back and reevaluate this table, and we have to ask the question: what happens when you remove, when you make each particle indistinguishable one from another? Well, since the total energy of the system is the same, the total energy of the system is this 9 epsilon, this column doesn't change, and all these different so-called macro states, there are 26 of them labeled by the letters in the alphabet, so you go from A to Z, right? All those states remain the same. The thing that happens is, because the particles are indistinguishable, now there's only one way to achieve each possible macrostate, right? So these degeneracies that were listed in this previous table, which were, took a fair amount of thought to generate those degeneracies, they completely disappear, and we now have a total of 26 possible states. When the particles were distinguishable, you'll remember that we had 2002 possible microstates. Now we've only got 26. And that completely changes the statistics, right? That completely changes the statistics. And to illustrate that, I'd like to just ask the question, on average, how many particles are there in each energy state now that the particles are indistinguishable one from another? Well, we're going to follow exactly the same program we did when we calculated the case for the distinguishable particles. The average energy, or the average number of particles in the energy state J, is basically going to be the sum over all the states. There's 26 different states. The degeneracy of each state has to be included. That's the G sub I quantity. We have to calculate from this table, we have to estimate the total number of particles in a particular state J, and we have to divide that by the total number of particles, which in this case is 6. So what we have to do is we have to use this table with these degeneracies to calculate these average numbers of particles. And so I just list the results of this calculation. You can go back and check it for one case. It's a lot easier now that the particles are distinguishable. If you run the numbers yourself, I'm sure you'll agree with the results that I provide. I sort of think these numbers are correct because if I add them all up, right, I ought to get 6, and I do, right, because 6 is the total number of particles available in the system. These just tell you on average how many particles will be in each energy level. It's very instructive, actually, to plot this new distribution. This new distribution is named after the Bose-Einstein theoretical distribution that was derived independently by both Bose and Einstein back in the 1920s. And it's very interesting to compare the average particle number in each energy level to the results that we obtained from the Maxwell-Boltzmann discussion that was based on this rather large table with these 2002 multiplicity levels, right? And that comparison is made in this graph. I just basically am plotting the occupation number, the average number of particles in each energy level as a function of energy. You can see the Bose-Einstein number compared to the Maxwell-Boltzmann number. And they're slightly different, even for 6 particles, right? Even for 6 particles, you can start to see a slight difference in the two distributions. And this difference is solely related to the fact that the Bose-Einstein particles are now strictly quantum mechanical and they are indistinguishable. Once they become indistinguishable, the multiplicity of these allowed energy levels drastically changes. When you change that multiplicity, you change the number of particles in each energy level. And in particular, what I like to call your attention to is the fact that the Bose-Einstein distribution, even for these 6 particles, which is by no means a large number of particles, right? The Bose-Einstein distribution at the lowest energy level, which is the 0 value, right, is actually slightly enhanced over the classical Maxwell-Boltzmann distribution. And this slight enhancement is going to be a characteristic signature of Bose-Einstein statistics, as we'll describe as the lecture unfolds. We can follow the same program for Fermi particles, right? So the Fermi particles now are going to have a spin 1/2, so let's pretend these are non-interacting electrons. And they are governed by Fermi-Dirac statistics. Fermi-Dirac statistics are named after Fermi and Dirac, who derived these statistics independently, again, back in the 1920s. We're going to consider the exact same system that we've considered for the Bose particles. We're going to now have 6 indistinguishable particles. They have spin 1/2, so they're fermions. We're going to give these particles collectively a total of 9 energy units, and we're going to ask what is the distribution of these particles in this 10 energy level system, okay? And we're going to compare that to what we got classically, because we're going to try to understand what are the differences that are imposed by the constraint that these particles are indistinguishable and have spin 1/2. Well, the new constraint is, right, that these Fermi particles, you can only put two electrons in the same, or two particles in the same quantum state, right? So the difference in quantum number has to come from the difference in the spin of the particles, and that just basically means that you only can get two electrons per energy level. Well, that has a drastic consequence on our table of possible states of the system. Because what we can do is we can look through this table, and any time we have an energy level that has more than two particles in it, right, that energy level or that state is going to be forbidden. So for instance, all these states here, which have 3, 4, or 5 particles in the zero energy state, those are all outlawed. Those are no longer possible. Any state that has more than 2 particles in the one energy level is also going to be outlawed. That's no longer possible. And the surprising thing is, if you look at this table carefully, you're going to find that there's only 5 states that survive this criterion. So these states are labeled N, O, P, Q, and V in this table. Those are the only states that can satisfy this this Pauli exclusion principle that's based on the spin 1/2 nature of the particles. Everything else is excluded, and so now, right, now the number of microstates that we have to consider is just 5. And so we've gone from 2002 for distinguishable particles down to 26 for Bose particles. For Fermi particles, we only have 5 possible states of the system. We can do the exact same thing we did for the bosons, right? We can ask, on average, how many particles are there in each energy state? We just have to take this definition for the average number of particles. And now the calculation is really simple, because instead of summing over all 26 states, right, there's only going to be 5 states that survive. And so this sum is only going to have 5 energy states associated with it. The degeneracy of each state is again going to be unity, so that simplifies the calculation. And these are the results I get. You're welcome to check, right? It's pretty simple to double check these numbers. And again, you like to believe that if you add the average number of particles in each energy level, if you add them all up, you're going to get 6. And in fact, if you do that sum, you'll find that everything works out. So I think I've got all the states identified and accounted for in this calculation. It's very useful to compare the results for the Fermi-Dirac particles to the Maxwell-Boltzmann distribution. This is the classic case, right? And what you see is, you see that there's actually a reduction of the number of particles in the lowest energy state compared to the classical situation. So classically, you ended up with, I think, about 2.3 particles in the zero energy level state. By imposing this condition on the spin 1/2 particles, right, that number drops down to about 1.7, 1.8. And the other important, or the other significant difference is that if you look at these higher energy states, there's a noticeable reduction in the number of particles that can exist in these higher energy states. And I try to make that point a little bit more clearly here, where I show the comparison now between Maxwell-Boltzmann, the Bose-Einstein, and the Fermi-Dirac for these energy levels 6, 7, 8, and 9. You see that the Fermi-Dirac statistics give you 0 particles in these higher energy states. Both the Maxwell-Boltzmann and the Bose-Einstein predicted non-zero values. So there's a significant difference, qualitative difference, not only at the 0 energy level, but also at the higher energy level for the Fermi-Dirac statistics. And what's amazing is that these subtle differences come out with just 6 particles in a rather simple system. So they're amplified. These differences are greatly amplified when you start to increase the total number of particles in the system. And what we're going to do next is we're going to derive an analytical formula that describes these probabilities that these various energy levels are populated. And we're going to have different formulas for the classical case. We've already done that. That's Maxwell-Boltzmann statistics. But we're going to write down the formulas for Bose-Einstein and Fermi-Dirac. Let's see, the next slide just makes makes the case again. I just ask, what's the probability that more than two particles exist in the lowest energy state? And I consider the three different types of particles that we're discussing. You can go back to these tables, right? And you can calculate, for the classical case, you can find that there's 686 different microstates that have more than two particles in the zero energy level. That's 686 out of 2002, which means that there's about 34% probability that you're going to have more than two particles in that zero energy state. If you do the same calculation for bosons, you find out there's about 12 states out of the 26 possible. That gives you 46% of all possible states have more than two particles in the ground state. So there's an enhancement for the bosons. For the fermions, it's impossible, right? You can't have more than two particles in any given state. So there's going to be no states that have more than two particles. So for fermions, probability that you're going to have more than two particles in that ground state energy is zero. So this again is just another way to reinforce this idea that the type of particle influences the type of statistics. The way that is done is by influencing the number of microstates possible for a given system. And when you follow that through, even at a very simple level, right, you start to pick up differences that are significant. So, what are the analytical forms for the quantum statistics when you start to let the number of particles get very large? And this is a very complicated derivation. If you really want to see the details, you can go to the website that I give in the footnote. In the appendix, I give some simple arguments that reproduce the derivations in the textbooks. My derivation is a little bit more intuitive. It's not quite as mathematical as the ones you typically find. And so you have a choice of reading the appendix if you want to understand how these formulas come about, or you can try to sort through the detailed mathematics that you can find in the textbook that we've chosen for this course. You have two options. Most of you are just going to be interested in the final result, and that's what I quote here. So this is this parameter f is a function of energy E, is telling you the probability that a particular energy state is occupied in a system. And it turns out that probability can be expressed in terms of a universal formula that contains two adjustable constants. One constant is zeta, the other constant is this parameter mu. And depending on different systems, zeta and mu will have different values. So zeta turns out to be either -1, 0, or +1. And I'll try to explain which value of zeta applies to which situation. Mu is a parameter that basically defines the zero of energy of the system. And mu has different values, again, depending on whether you're talking about classical gas atoms or photons or electrons. So the appropriate values for mu for a few simple, the appropriate values for both mu and zeta are listed here for a couple of simple situations. And in the next slide, I just summarize the results in a convenient table, and I include a graph so you can visually see with this distribution function f of e is trying to convey. So we've got three situations that we've discussed. We've discussed the Bose-Einstein particles, we've discussed the classical Maxwell-Boltzmann particles, and then we've discussed electrons, which are governed by the Fermi-Dirac Statistics. And depending on which system you're interested in, zeta and mu have different values. And what I've plotted is the shape of these distribution functions for the three different situations. So the simplest one to comprehend is the Maxwell-Boltzmann distribution. This is the exponential decay of particles at higher energies, right? And that's something that we've discussed in the context of the Maxwell-Boltzmann distribution of velocities or energies of particles in a classical gas. In contrast to the Maxwell-Boltzmann distribution, the Bose-Einstein distribution essentially agrees at higher energies, but as you get to lower energies, you find that the Bose-Einstein distribution shoots up, gets very large, and significantly deviates from Maxwell-Boltzmann. This is just telling you that for low energies, if you have a gas of Maxwell-Boltzmann particles, right, or a collection, if you have a collection of if you have a collection of Bose-Einstein particles, you're going to find an increased tendency for the particles to exist in lower energy states compared to the classical case. When you deal with electrons, with fermions, then you have to use the Fermi-Dirac distribution function. The Fermi-Dirac distribution function saturates at unity when you're at energies much lower than this characteristic energy mu. And as you go to energies much higher than this characteristic energy mu, it turns out the Fermi-Dirac statistics essentially match those of Maxwell-Boltzmann and Bose-Einstein way out here at high energies. In the middle, there's a transition from a unit probability. So down here at these lower energies, the states that exist down there are populated with unit probability. Right at when the energy E is equal to this parameter mu, the probability of occupation is equal to 1/2. And then as you go out to higher energies, when E minus mu is much greater than KT, right, then the probability that the states out there are occupied goes to 0. So this is kind of the culmination of our discussion of statistics. A lot of textbooks just give you these results and they don't give you any intuition about where they came from. The approach I've tried to follow is I've tried to cook up a simple enough system that you can apply these ideas and get a much better intuitive understanding of what the fundamental differences are between these three very important distribution functions. I wanted to say a little bit more about the Bose-Einstein distribution because it's been a topic of considerable interest in the literature during the past 10 or so years. I just want to make the point that if you plot the Bose-Einstein distribution function, this is the f of E, right, and you just plot it as a function of temperature, what you find is that as the temperature decreases, the sharpness of this curve increases dramatically. And what this is just telling you is that as you go from, let's say, 300 Kelvin to, let's say, 50 Kelvin, the probability that these higher energy states that are actually occupied, that probability gets very, very small. And in the limit, as T gets smaller and smaller, what you find is that this Bose-Einstein distribution function is very, very narrowly peaked around this zero energy level. And in fact, what we say that if you can cool the collection of bosons, so if you have n bosons, you can cool them down to a low enough temperature, they actually condense and they form a Bose condensate. And all the particles have a very strong tendency to be in one single quantum state. right? So you've got, let's say, a collection of N bosons, N atoms with 0 spin. If you cool those atoms down to a low enough temperature, they'll condense into a new quantum state, which is referred to as the Bose Condensate, and that Bose Condensate forms a single quantum state for the entire collection of N atoms. So this has been understood, I think, since the 1930s. The question is how to achieve it, and that's proved to be a little bit more difficult. It was finally achieved in the late 1990s. Nobel Prize in Physics was awarded to the 3 gentlemen who actually experimentally demonstrated this Bose condensate. And the reason it's interesting is because if you go back to our discussion of quantum numbers, for instance, of particles in a 3-dimensional box, each quantum state can be represented by a triad of quantum numbers nx, ny, and z. So each dot in this diagram represents an individual quantum state. What these Bose statistics are telling you is that if you cool this system down to a low enough temperature, all these quantum states condense into this lowest energy state, which is represented by this black dot down here. And this lowest energy state is still a quantum state, but it just has all these other particles that were in these higher energy states present. So there's a huge condensation of particles into one massive quantum state, which has very interesting physical properties. And that's a topic of intense interest in the physics community, even as we speak. So, by way of summary, I wanted to just emphasize a unifying theme that I hope will tie together some of the lectures that we've given in the last couple weeks. And this unifying theme is the calculation of the number of occupied states in a given quantum system. And this number of occupied states is basically related to the density of available states. And the density of available states I've used the symbol G throughout these lectures to represent. So G depends on the particular system that you're interested in. The system does not have to be classical, or does not have to be a quantum system. It could be a classical system, right? But each system that you consider is going to have a different density of states, and you need to know that in order to calculate how many of those states are actually occupied. In addition to knowing the density of available states, you've got to know the probability that that particular state is occupied, and the probability of occupation is given by this function f. And this function f is there's only 3 choices for it. It can be either a Bose-Einstein distribution, it can be a classical Maxwell-Boltzmann distribution, or it can be a Fermi-Dirac distribution. So F describes the probability that a state is occupied. G tells you how many different states there are. If you multiply these 2 things together and multiply by an energy interval delta E, right, that tells you how many states at that particular energy are occupied within this energy interval delta E. So this formula, which I think I included in the first slide maybe 2 weeks back, right? This formula is the unifying theme that sort of links together all these discussions that we've had. We've had discussions that consider both these quantities separately, but the payoff is that when you combine them in this way, you can actually start to tell something about the number of particles in different energy levels for different systems of interest. And just to sort of reinforce that notion, if you go back and you look at my lecture notes, there's at least three separate occasions where we've written down results, and these results can be understood in terms of this unifying theme, right? If you recall back in the first week of the course, we talked about Planck's blackbody density of radiation field. Well, it turns out if you write that formula down, this prefactor here is telling you something about the density of the photon states, And this factor here is telling you about the occupation probability of those states. So this is the Bose-Einstein distribution function, which we now appreciate, but which Planck didn't have a clue of back in 1900 when he worked this out. If you go back and look at the Maxwell-Boltzmann distribution function you have to look at lecture 9.02, right? If you look at the appendix of that, this exponential factor here is the Maxwell-Boltzmann distribution. That's the probability that the state of given energy E is occupied. This prefactor here is basically a density of states term, which tells you how many atom states are available, how many molecule states of a particle moving in 3 dimensions are available as a function of energy E. And then lastly, in another week or so, we'll do the case of free electrons, and we'll come up with a formula that looks like this. Again, it's the same general form, right? We've got a prefactor that tells us the density of states, and then we got the Fermi-Dirac distribution function that tells us the probability that those states are occupied. So, I'm running a little late. I have to end this lecture, but this ends our discussion of statistics, both in the classical world and also in the quantum world. And what we're going to do now next is we're going to move into a discussion of what happens when you take a collection of atoms and condense those atoms into the solid state to form a solid. And what we're going to try to do is we're going to try to provide a basis for you to understand the nature of the electron states that exist when you take 10 to the 23rd atoms in the gas phase, condense those atoms down into a solid metal or semiconductor, and then ask what happens to the electron energy states of each of those atoms as they condense down. So that's going to be the topic of discussion for the next week or so, and it'll hopefully clarify your understanding of electron states and solids. So thanks for listening to these lectures on statistical mechanics. We've just basically touched the surface of the topic. There's a lot of information, a lot of useful calculations that you can do if you understand these basic principles, and I hope you spend a few minutes working through some of these examples that I gave in this lecture to sort of reinforce the notion of the difference between Bose-Einstein Fermi-Dirac statistics from your classical statistics. So we'll see you in the next lecture. We'll start a new set of topics in this coming week.